Good afternoon, everybody. This is a video that's going to cover section 10.R.1 and 10.1, which is the last section in the graphing unit. So it's following the stuff from chapter 2 that we did, and it's going to kind of tie everything together because we're back to talking about linear equations. This time we are going to be solving systems of equations in 2 and 3 variables. And we're going to run into several different situations with these different types of equations. So we're going to kind of talk about them as we go. But before we get into actually solving them and the methods for solving, we're going to talk about what it takes to be a solution to a system of equations. So the first thing we're going to do is check. And there are two fairly basic examples here. So we are going to be looking to see if these ordered pairs, well, I'm actually just going to do this one. We're going to ignore that one. We'll do this one. And if this ordered pair is a solution to this system of equations. Now, in order for it to be a solution to the system, you have to be able to substitute in the x and y coordinate for both equations, x and y variables, and have yourself end up with a true statement in both cases. So if you get a false statement for either one of the equations, then it doesn't matter what happens in the other one because it has to be true for both. So we're hoping that when we plug in this x and y, we get true statements for both of these equations. So we're going to check. We start with the first equation. We're going to plug in -3 for x and 3 for y and see if we get a balanced equation. So we're going to simplify this a bit. 5 times -3 is -15. 3 times 3 gives me +9 plus 6. And we want to know, is this 0? Well, -15 plus 9 plus 6 is 0. And 0 equals 0 is always true. So that one checks for our first equation. If we would have gotten something that was false, like 3 equals 0, then we could stop right there. There's no need to go any further because if it's false for this one, it doesn't matter. So far so good. That means we continue on our little quest to find out if this thing works. Going into the second equation, same ordered pair. 2 times -3 minus y is also 3. And this time it's +9 equals 0. Now, 2 times -3 gives me -6. Then we've got -3 more plus 9 equals 0. So when I simplify this left-hand side, -6 minus 3 is -9, plus 9 is 0. And again, 0 equals 0 all the time. So it checks for the second one as well. Since they both check out and are true, yes, it is a solution. Again, if it does not check for either one, then the answer is no. So you can use the little checking method anytime that you want to check an answer that you get, either graphically or algebraically. Also, if you hear me drinking or shuffling papers around, it's because I'm following these notes that I have written out, and also because I talk all day and my throat gets dry. So I might be drinking quite a bit. All right, so now we're going to get into actually solving. There are 3 methods that we are going to use in this course for solving. Those are not the only 3 methods that exist. They're just the only 3 that we are going to use. So the first method that we are going to look at is solving systems by graphing. Now, I'm not going to lie, graphing is not my favorite thing to do for solving systems. And the reason is because if you get a solution that is anything but integers, it's nearly impossible to figure out what the solution is actually supposed to be. If they don't intersect on a nice point, then you can't really tell on a graph if it's 1/3 or 1/2 or 2/5. So it's difficult to find an exact answer unless it ends up being integers, or one of the special cases, I guess. So not really my favorite. It is possible. If you have a graphing calculator, I recommend using the graphing calculator for these ones. And if you get something that doesn't fall on an integer, I recommend doing it algebraically to check. So that's why I kind of typically myself would avoid this method, just because I want to make sure that if I get a fraction or decimal answer, I can actually find it. But what we're looking for in solving systems by graphing is for the intersection of our two lines. The intersection is the point where the two lines touch each other. And if we have an intersection point, that intersection point is our solution. There are also two other situations that we can run into when we are dealing with solving systems by graphing, because you don't always get two lines that intersect at one nice, neat point. So the two special cases come when we have parallel lines and the same line twice. By definition, parallel lines are two lines that never intersect. So if they don't intersect, there's no intersection point. And if there's no intersection point, we can't have a solution. So you'd get no solution there. If they intersect at one point, it's the ordered pair where they intersect. So we just have to kind of see. And then the last situation for special cases is when you have these two equations, but when you plot them, they happen to be the same exact line twice. When they are the same line twice, we get infinitely many solutions, which has a special little way to write it as an ordered pair using variables and expressions. So we're going to take a look at that also when we see this situation pop up. Otherwise, it's no solution, or it will be an ordered pair where you have your x and y coordinates. So that's what we're looking for here. So let's see. We're going to scroll down here. We have a couple different examples to solve our systems graphically. Now, you can use any method that we've used so far for graphing. Whichever you prefer, you can make a table, you can use the x and y intercepts, you can use the slope and y-intercept, whatever you like. A lot of people like to use the slope and the y-intercept. So I'm going to go ahead and put these equations in slope-intercept form if possible, and then graph it in that way. So my first equation here, 2x plus y equals 5. To isolate the y, I subtract 2x over. That gives me y equals negative 2x plus 5. And now I graph this thing using the slope and the y-intercept, which is 5. 1, 2, 3, 4, 5. There's my point. And I'm going to go down 2, right 1, down 2, right 1, down 2, right 1. I'm just putting extra points on here so that I can try to be real careful. Because when I draw these things, they never end up looking right. Maybe I can use the line tool and actually have it work. Good Lord, I don't know. I'm nervous. Like this. And then, oh, like that. Oh my gosh, I think it actually worked nicely. That never happens. Yay. All right, second equation. To isolate the y, we're going to divide by negative 3. Divide negative 3. We get negative 1/3. That doesn't look nice. Got a little cocky there. Negative 1/3 x equals y. In this case, the slope is negative 1/3. The y-intercept is 0, 0, because this doesn't have a b value there. And if there's no b value there, that's okay. It just means it starts at the origin. All right, so there's my point. This time we go down 1, right 3. Oh, and look at that. We're already touching that line. So this one will have an intersection point. Let's see if I get lucky with the graph again. Oh, not too bad. Look at that. And those two lines graph nice and neat. And we get lucky because we do have one single intersection point. So I'm going to highlight it right here. This is our intersection point right there. And since we have an intersection point, that point is our solution. So when we go to write our solution, we're going to put the intersection point down. The solution here is +1, -3. So that is what we're looking for. And when you have intersecting lines, you get one of these nice little intersecting points. This second one, I'm wondering if we're even going to be able to tell because I can already tell that it has a fraction in it. But we'll see. All right, our second equation, our second equations, I guess, is 3y equals 9 and x plus 2y equals 11. Now, 3y equals 9 is one of our special lines because when you isolate y, you get y equals 3, and that is a horizontal line. Horizontal lines are straight sideways through, in this case, y equals 3. So we're going to go up 1, 2, 3, and then our line is going to be right here on 3. So here's our first line, it's horizontal. We're going to do the same thing just with the second line. And the second line, we don't get as lucky. When we isolate y, we subtract the x over. I get 2y equals -x plus 11. And when I divide by 2, I get -1/2 x plus 11 halves. Now, the slope in this case is -1/2, which is fine because we move single units. We don't have to worry about a fraction for slope. But our y-intercept is 0, 11 halves. And 11 halves is 5 1/2. So we are going to have to be super careful when we're doing this and just hope for the best while we're going through this. So I'm going to graph 11 halves, which again is 5 1/2. So 1, 2, 3, 4, 5 1/2-ish right there. And this is going to be hard enough because this thing, every time I try to make a point, it doesn't do. And now when we follow the slope, we have to go down 1, right 2. So when I go down 1, I'm still in between because down 1 puts me at the next half mark down here. Right 2, down 1, right 2, oh gosh. Down 1, right 2, right here. So this is not looking good for us. Maybe the line will help whenever I put the actual line on here. Line. Not, okay, not terrible. There it is. Let me see if I can, is it easy to see when I go out? There it is. Okay. Actually, somehow, by some miracle, it looks like this thing ended up on an actual point. And hopefully I'm not wrong about that. But it looks like there's the point right there, which actually falls on the grid line. So awesome. I'm hoping this is the solution and it's just not that my graph is off a little bit. But it looks like our ordered pair is 1, 2, 3, 4, 5, 3 as our solution. So fingers crossed that that's right. It looks right. The point is, you're looking for that intersection point. Now, I already mentioned this stuff. If the lines don't intersect, it's parallel. There's no solution. If it's the same line, they always intersect. So there are infinitely many solutions because any point that works for the first one works for the second one as well. They work the same. Now, there is a classification system involved here, and at times Hawks may ask you for the classifications. So the classifications are going to come into play after you solve your equations. It's based on what your solution is for each one. So this is probably going to come into play at times whenever you're going through your homework. And when you classify solutions, you look at what the solutions look like for your example. So if your system of equations has at least one solution, meaning it's got an ordered pair or it's the infinitely many solutions one, that means there is a solution and the system is considered consistent. If your equations are parallel, then they have no solution and the system is considered inconsistent. If you happen to have the situation where you have infinitely many solutions, not only is that system consistent, but it's also considered dependent. So there are several different classifications you can see, and they kind of all apply in a different way. So just kind of keep this in mind in case you're asked about the classifications for these lines. So that's solving systems by graphing. Now, there are two algebraic methods that we're going to talk about: substitution and elimination. The substitution method is the first method, and the substitution method is best used when you have an equation that already has a variable isolated, or you have an equation where you've got a variable with a coefficient of 1. The reason why it's good in that case is because those ones are the easiest to isolate. And in order to use the substitution, you have to have an isolated variable, because you're going to substitute in the place of that variable in the other equation. The whole point in doing this substitution is to create an equation with a single variable in it so that you can then solve that equation and get an actual value. If you don't have an equation with only one variable in it, you can't solve it. So we have to get a solution here. And the way we're going to do that is by creating a good situation with only one variable so that we can isolate. Now, once you have your first variable done, then you can substitute that value into either one of the original equations and solve for the other value. If you get two solutions for your x and y, remember you have to put them into an ordered pair as your final answer. We can't leave them separate because the rules say ordered pairs are what we use for our final answer. So I want to take a look at a couple examples with substitution. And my first example here has these two equations in the system. Now, neither one of them already have an isolated variable, but the second equation has a y coordinate that has a coefficient of 1. So I can easily isolate y by subtracting 4x over to the other side. And that's where I'm going to begin. Isolate the y. To isolate the y, I subtract 4x over. I get negative 4x plus 3 for my y. Now, y and this expression are equal to each other, which means that they are interchangeable anytime I want them to be. And I want them to be right now, because I'm going to take this expression that y equals and I'm going to put it way over here in the other equation in the place of the y. So that instead of seeing 2x minus y, I'm going to see 2x minus this expression. Negative 4x plus 3 equals negative 2. So I have just replaced the y with the expression that it's equal to, and I'm allowed to do that if I want to. Now, if you look at this equation that we've created now only has one type of variable in it, which means that it is solvable. We can isolate our x. So we're going to go through all the steps for solving linear equations that we used back in section 1.5, which was at the very beginning of the semester. And we're going to start by getting rid of the parentheses. To get rid of the parenthesis, we distribute this negative, which gives me 2x minus negative 4 means plus 4x minus 3 equals negative 2. We're going to combine these like terms here. That gives me 6x minus 3 equals negative 2. It's not negative 2. It's positive 2. Hold on. Let me erase this negative before I screw everybody up and nobody knows what I'm talking about. Can I erase it? There we go. Get rid of this. It's just 2. Sorry. Now you're probably all like, where'd she get negative? It's not. It's 2. Okay. Now that I have fixed that and the answer will look right, we're going to isolate our x, add the 3 over. That gives me 6x equals 5. And then when I divide both sides by 6, unless Hawk says I'm allowed, I'm leaving this thing as a fraction. So for practice, I'm going to leave it as a fraction. If they say it's okay to write your answer as a decimal, then go for it. But for now, we're going with 5/6. So that's the first part of my solution. It's the x coordinate of my ordered pair. But, excuse me, these ordered pairs need to have an x and a y. So I've got to find the y coordinate. And lucky for me, I have 1, 2, 3 different equations that I can use to find it. Any one of these equations is going to give me the same y coordinate, so whichever one you like the best, you can use. I typically like the one where the variable's isolated, but again, that's a personal choice and it doesn't matter. So I'm going to go into that isolated equation because that's the one I like. So I've got y equals negative 4 times 5/6 plus 3. Negative 4 times 5/6 is negative 20 over 6 plus 3. Now this will simplify a little bit, and you can simplify it here or you can simplify it at the end. So whichever one you prefer is fine. Negative 20 over 6 simplifies to negative 10 thirds plus 3 over 1. Now I've got to have a common denominator because anytime we add and subtract, we need a common denominator. So my LCD is 3, and that means I got to bring a 3 over here. So I'm looking at negative 10 thirds plus 9 thirds. And negative 10 thirds plus 9 thirds is negative 1 third. And that's your y coordinate. Now we have our x and our y. And to write our final answer, we want to put it as an ordered pair. X, comma, y, 1/3. And there's our ordered pair. So we do isolate, then substitute, solve, substitute, solve. We're going to do something similar for this second equation, but the second equation looks a little bit different because we don't really have anything jumping out at us to isolate. In these equations, we don't have any one of our variables having a coefficient of 1. So we basically just have to pick what we want to do. In the last one, I think we isolated y, so let's isolate x just to be different. So I'm going to isolate x in my first equation. All right, so I'm going to get this x by itself. I start by subtracting the 6y over. That gives me 3x equals negative 6y minus 12. And then I have to divide everything in this equation by 3. So that gives me x equals negative 2y minus 4. That's kind of nice though, because at least we don't have any fractions starting off. We don't know what's going to happen, but right now it looks pretty good. So now I have my x isolated, and I have an expression over here for my x. That means these two things are interchangeable. And I want to exchange this x over here with this expression. So I'm going to put that right in there. And now it's going to look like 2 times this expression, negative 2y minus 4, plus 4y equals negative 8, instead of having the x in there. Now, this equation, you should notice at this point, only contains y's, which means that we can solve it for y if we follow the steps for linear solving, beginning with distribution, negative 4y minus 8 plus 4y equals negative 8. Now, in the next step, we would combine like terms. And in this situation, when I combine my like terms, they actually happen to cancel each other out. When the terms cancel each other out, we are not going to be able to get a traditional ordered pair solution. It's just not possible. So we have one of our other special cases. To figure out which one it is, we have to look at what remains in the equation after the variables have canceled. In our equation, we're left with negative 8 equals negative 8. Now, this statement here is a true statement. When we get a true statement, that means that anything that you would want to plug in for x and y is going to work for both equations. There are infinitely many solutions. Any ordered pair will do. Now, at times, you're going to have to write this in a very odd way, okay? So what I want to do is write an ordered pair where I let the x be the expression that we created in terms of y, negative 2y minus 4, comma, and let the y coordinate just be the letter y. You can also go the other way where you let the x coordinate be x, and then for your y coordinate, you put in your expression when you isolate y. And it will kind of depend on what you're asked for, which one you're going to want to put in. This one is in terms of y. You can also be asked to put it in terms of x. So it's an odd way to have to write it, but it's fine. That just lets you know that this thing here is what y equals. And you can plug all kinds of stuff in there. So there's your infinitely many situation. Now I want to come down here and talk about the elimination method. And we're going to do one example using the elimination method because we're going to do several other ones where we involve the elimination method. So I'm going to do one that's straightforward and then kind of apply it to several other things. Now, the elimination method is a method that is used mostly when the equations are in standard form. What we like to have is equations that are in standard form where there's no fractions or decimals or anything funky going on, so that all the terms are nice and neat and integers and line up nice on top of each other. The reason why we want them to all look like this is because the goal is to multiply one or both of the equations by some constant to get the same coefficient with opposite signs in front of one of your variables. Now, you get to decide which variable you want to eliminate. There's no rule about it. If you have no clue where to start, just pick one, and whichever one you pick, you go with. Once you decide which one you want to eliminate, you're going to find the least common multiple for those two coefficients. And then whatever it is, you're going to multiply by a constant to obtain that least common multiple. The one little trick that you have to be concerned with is that your coefficients have to have opposite signs. So if they don't have opposite signs to begin with, you are going to have to use a negative in at least one of your two multiples. If you don't use a negative in one of those things, then when you do your distribution, you'll have the same sign on your coefficients, and that won't cancel. You have to have opposite signs in order to cancel. So we want to make sure that we not only find the LCM, but we involve a negative to make sure they have opposite signs. If they already have opposite signs, you don't have to worry about that. So it's nice when they already have opposite signs, but we'll just have to kind of see what happens, because there's all kinds of stuff that can crop up, so we'll just see. So let's see here. The first example is a little bit more basic, so I'm going to go to the second one. And again, we're going to get more practice here. So I'm going to start with this guy. Now, the reason why I wanted to start with this one is because it's close to being in standard form, but we have fractions going all around here. And standard form is not allowed to have any fractions. So I have got to start by getting rid of all of these fractions in these equations. And if you remember the little trick that we used, get rid of denominators, you find the LCD and then multiply all the terms by the LCD. So for example, in this first equation, the LCD between 3 and 5 is 15. So all the terms are going to get a 15 so that I can cancel out those denominators. 15 cancels the 3, I'm left with 5. 5 times 2 is 10x. 15 cancels the 5, I'm left with 3. 3 times 3 is 9y. Now on the other side, there isn't anything to cancel, so I have to actually multiply 15 times negative 17, and I get a big number, negative 255, negative 255. But that's okay, because it's all going to end up coming out in the wash anyway. All right, on the other side, we've got denominators of 2 and 3, which means the LCD is 6. And I'm going to multiply everything by 6. 6 here, 6 here, and 6 over here. All right, let's get my green here. 6 cancels the 2. There's 3 left. 3 times 1 is 3x. 6 cancels the 3. There's 2 left. Negative 2 times 1 is negative 2y. And on the other side, negative 1 times 6 is negative 6. So this one's a little bit more basic and nicer to look at, but either way, at least they all have integers now. So now that I have my nicer equations, I'm going to write them one on top of the other. 10x minus, plus 9y equals negative 255. And 3x minus 2y equals negative 6. Now, from here, I get to decide which one of my two variables I want to eliminate. And it does not matter which one you pick. So you can kind of just pick whatever you want. When I'm picking, I like to look for different things that would make my life easier. One of the first things that I look for is, do they have the same coefficient already? Because if their coefficients match, all you have to do is multiply one of the equations by a negative. We don't have that here. The second thing that I look for is if they already have opposite signs, because then we don't even have to worry about the negative. So in this case, my y's have opposite signs, so I'm going to eliminate y. To eliminate the y, I need to find the least common multiple between its coefficients. The least common multiple between 9 and 2 is 18. So I'm going to use 18 to do it. I'm going to turn both of these coefficients into an 18. I am not going to mess with the signs because they already have opposite signs. So I'm in good shape there. So I'm going to start by turning 9 into 18. And to do that, I have to multiply by 2. And then I'm going to turn 2 into 18. And to do that, I multiply it by 9. Again, do not use a negative. We already have opposite signs. So now that I know what I have to multiply by, I'm going to go ahead and multiply it through. I distribute. 2 times 10 gives me 20x. 2 times 9 gives me 18y. And 2 times negative 255 gives me negative 510. On the other side, I distribute again. 9 times 3 gives me 27x. 9 times negative 2 gives me minus 18y. And 9 times negative 6 gives me negative 54. Now, as soon as you have a variable that has the same coefficient with opposite signs, you know that you're ready to combine the equations. So I'm going to combine these two equations together. 20x plus 27x is 47x. The 18y's cancel, which means there's no y left in this equation. And negative 510 minus 54 more is negative 564, which I know is a huge number, but hopefully it will divide by 47 and make our life easy. So we're going to isolate our x by dividing by 47. And lucky for us, negative 564 divided by 47 is negative 12. So thank God for that. Now, as soon as we have one of the two variables solved, now we're going to go back to the substitution method. You do not have to eliminate again to find x. You can, but it takes more time to do it that way. So I'm not going to do that. I'm going to substitute. Once again, I have several different options for my substitution. I can go back into the originals, the ones I made without the fractions. I can go back into these pink ones here that I made with the constants. It doesn't really matter. Since this one seems the most out of the way and simple, I'm going to use this one. So I've got 3x minus 2y equals negative 6, and I'm plugging in negative 12 for my x. 3 times negative 12 minus 2y, equals 6, negative 6, goodness. Simplify, 3 times negative 12 is negative 36, minus y equals negative 6. There, that's a little bit better. And now I've got 2 steps to follow. Add 36. That gives me negative 2y equals 30. And when I divide by 2, y equals negative 15. So awesome for us. We got an x, we got a y. Let's put them together. Negative 12, comma, negative 15. And there's my ordered pair. All right, I have to hit the pause button here because people keep coming to my door. So I'm going to pause here for a second. I will pick up a second video to finish this handout out that has the 3 equations, 3 unknowns, and a couple word problems so you can see how the applications work. So pause and click the second link for the new video for the second half of this stuff.